Okay, hello everyone. Today we'll be talking about Chapter 3, Organic Molecules and Functional Groups. And the main thing to take away from organic molecules and functional groups is that generally we're going to have a carbon skeleton, so anything made up of just carbons, aka our parent chain, which we'll talk about a little bit later, and whatever part that is not just made out of carbons or hydrogens using only single bonds. Carbon-carbon double bonds and carbon-carbon triple bonds are considered functional groups. So when we talk about carbon skeletons, generally we're just talking about carbon-carbon single bonds that are fully saturated with hydrogens. Now, what's important to note here is that the functional group, or the different parts of the functional group, are what is actually the reactive portion of a carbon molecule. So, for example, if I just had a carbon chain, such as this is not very reactive because we don't have any functional groups. However, if instead I had a bromine at the end, that would make this something called an alkyl halide. And you can notice here that an alkyl group or an alkane group is just whatever we have carbons single bonded to carbons saturated with hydrogens. The halide group is the halogen at the end. So this Br could be an F, a Cl, a Br, or an I. That's what makes this an alkyl halide. The alkane group, which is the R group, attached to a halogen, which you'll mostly see as X. Okay? All right. And so then when this molecule goes through a reaction, the part of the molecule that's going to go through that reaction is going to be this end that contains the bromine. Okay, so the functional group is generally going to be the place that a reaction is going to proceed for a specific compound or molecule. Okay, and so there are different types of functional groups. They're mainly divided into 4 types in this PowerPoint, I believe. The first type are the carbon-carbon bonds, the functional groups that deal with carbon-carbon bonds. So when we see alkane, notice we end with A-N-E. All this means is we have carbons single bonded with other carbons and hydrogens. This is what we talked about earlier, which was our R group, which is just our carbon skeleton, okay? And alkene, E-N-E, has a carbon-carbon double bond, okay? And so then this is what sort of sets it apart from an alkane. And then alkyne, Y-N-E, has a triple bond, sets it apart from an alkene or an alkane. And then an aromatic compound is something that's a little bit different. You'll go through this more when you talk about Orgo 2, but generally an aromatic compound is a cyclic compound that is fully conjugated with double bonds. That essentially means that every other bond has either a double bond or a lone pair available to it. And again, like I said before, you'll go over this more in organic chemistry too. All right. So when we're talking about carbons and hydrogens, generally we'll call them a primary carbon, which is this 1 degree that you see here, but the real word is primary, a secondary carbon, a tertiary carbon, or a quaternary carbon. And then you can see the same thing with hydrogen, a primary hydrogen, a secondary hydrogen, and a tertiary hydrogen. What's important here is to note that the designation primary, secondary, or tertiary is not dependent on how many bonds the hydrogen has. Rather, it's dependent on how many carbon-carbon bonds that it's attached to. So for example, in this primary carbon, this hydrogen is attached to a carbon with a single carbon-carbon bond. A secondary hydrogen is attached to a carbon with 2 carbon-carbon bonds. And finally, tertiary, 3 carbon-carbon bonds. And notice here how we do not have a quaternary hydrogen. This is because, again, just a reminder, carbon can only have 4 bonds. And for us to even have a hydrogen, one of those bonds has to be taken up by a hydrogen, so we can't have a quaternary hydrogen. On the other hand, we can have a quaternary carbon because that designation, primary, secondary, tertiary, quaternary, is dependent on how many carbons that specific carbon is attached to. So in this case, quaternary carbon, 4 carbon attachments, tertiary, 3 carbons, secondary, 2 carbons, primary, no carbon, or 1 carbon, sorry. And then there's one more designation called a methyl carbon. Essentially, a methyl carbon is a carbon with no carbon-carbon bonds. Generally, you'll see it written as CH3 or maybe CH4, but honestly, the CH3 is more likely to be seen. So we have methyl carbons, we have primary carbons, secondary carbons, tertiary carbons, or quaternary carbons. And then we can have primary hydrogens, secondary hydrogens, or tertiary hydrogens. Okay, so let's continue on to the second main group. So the second main group is functional groups with carbon Z sigma bonds. All this means is we have a carbon single bonded to some sort of heteroatom, which is our stand-in here, Z. So a CZ bond is a carbon single bonded to a heteroatom. And as a reminder, a heteroatom is simply any atom that's not carbon and not hydrogen. So you can see here, what I talked about earlier was an alkyl halide. You can't really see it here because it's being sort of blocked by this graphic here, but it's generally the R attached to an X. Again, our R is just our carbon background, our alkyl chain. X is any halogen. And then these are like what the groups are named. So a halo group, a hydroxy group, an alkoxy group, an amino group, a mercapto group, and an alkyl thiol group. So a lot of these names, these group names, they are important, but honestly, they're less important overall than understanding what makes an alcohol or an ether or an amine or a thiol or a sulfide. It's more important to be able to recognize the main name of the chain rather than being able to name the groups a part of them. Okay? So we talked a little bit about alkyl halide. An alcohol is simply anything with a hydroxy, also known as an OH group. So if we have a carbon chain with an OH on it, that's an alcohol. Something important to note is that an alcohol has an OH group bound to an sp3 hybridized carbon. So this carbon that the OH is attached to has to have 4 bonds total. This is important when we get into the carboxy subset of functional groups, which has an OH attached to a carbon with a double bond to an oxygen. So this would not be considered an alcohol because this carbon here that the OH is attached to is not sp3, it is sp2. And we'll get into this a little bit further. It's just important to note that, again, we're talking about carbon heteroatom single bonds, which means sp3 hybridized. The next thing I want to talk about is an ether. An ether just has an oxygen flanked by 2 carbon-based groups. So we have an oxygen in the middle, and we can say that we have 2 carbons on this side and then a single carbon on this side. This is an ether. So all this is an oxygen flanked on either side by carbon groups. An amine is a little bit trickier, I guess. It's just any group that has nitrogen attached to it. So you can see here we have R single bond to NH2, R2 single bond to NH, or R3N. So these structures look like this. So R bound to N, which has single bonds to 2 hydrogens. Or instead of having 2 hydrogens, you have 2 R groups with 1 hydrogen. Or instead of any hydrogens, you only have R groups, okay? So these are still made up of single bonds. It's just the number of hydrogens can vary for an amine. So if we see something like a long chain attached to an N, which is attached to another chain, attached to an H, this is an amine. This example here is also an amine, and so on. So an amine is just any R group with a nitrogen attached to it, and that nitrogen can be attached to any number of other hydrogens or other R groups, okay? And then a thiol, you may see this when you talk about amino acids, such as cysteine. And we can see here that a thiol has an SH group, also known as a mercapto group. So an R group here, SH. And finally, a sulfide. So you can see that thiols and sulfides are sort of akin to alcohols and ethers, where a thiol would be similar to an alcohol because you just have an SH group, and a sulfide will be similar to an ether group because you have an S flanked by 2 R groups, okay? So I want to talk about one more thing, going back to the amine group. We can see here that we can designate amines primary, secondary, tertiary, just like we designated hydrogens and carbons primary, secondary, tertiary. This is based on the same overall idea that the number of carbons that the nitrogen is attached to, so the number of R groups it is attached to, determines whether it's primary, secondary, or tertiary. So a primary amine, only one carbon bond, only one R group. Secondary, 2 R groups. Tertiary, 3 R groups. Now, there's something I want to talk about a little bit when we're talking about alkyl halides. We can also sort of use this, this idea of primary, secondary, tertiary with alkyl halides. So I'm going to use Br as my halogen example here. Let's say that we have Br that looks like this. So this is our alkyl halide. And we would consider this a primary alkyl halide because if we look here, the carbon that the bromine is attached to, reminder that every point in this chain and every end to this chain is a carbon. So we see here that this carbon this bromine is attached to one other carbon. So this carbon here is primary. We would consider this alkyl halide a primary alkyl halide. In a similar vein, if we had our Br sticking up right here, then that carbon it's attached to would be attached to 2 other carbons, and it'd be secondary, and so on with tertiary. Okay? So now let's talk about the next group, and this is called a carboxy functional groups. So the carboxy functional groups have a carboxy carbon, which means just a carbon double bonded to an oxygen. Okay? We can see here that this is why, or this carboxylic acid, this is why it's important to recognize that alcohols have an OH bonded to an sp3 carbon. Because in this example, with a carboxylic acid, we see we have an sp2 carbon bound to an OH group. So we would not consider this an alcohol, and instead it's a carboxy group. Okay? So here are the different carboxy groups. Again, it's sort of the same situation as all the other ones. We're an aldehyde. I always remembered aldehyde because this is one of the few functional groups. I can't really think of any off the top of my head other than thiols that have an H in them. So an aldehyde, it has an H in it. We have our carboxy group bound to an H. A ketone, I don't really have anything to remember this off the top of my head. The carboxylic acids and ketones and aldehydes are sort of the main big 3 that you kind of need to worry about right now in this particular Organic Chemistry 1 class. Where aldehydes, we have that H in the name, so it's going to have an H attached to its carboxylic carbon. A carboxylic acid, we think of this as acidic, and generally acidic things have a proton to donate. And remember, if you recall, when we were talking about acid bases, an OH is more acidic than a CH. So in this case, we have and also a carboxylic acid is stabilized by resonance. So this guy is pretty acidic. And so that's why it's called a carboxylic acid. And I don't really have any big mnemonics to remember ketones. I'm trying to think of any right now, but if you can think of one, just leave it in the comments or just message me because that'd be really cool. And so then those are sort of the big 3 for this class, but there are also esters, amides, and acid chlorides. You'll talk about these a little bit more in Orgo 2, but I do want to touch on them now. So esters, they're similar to carboxylic acids, but instead of having an OH group, we have an OR group. So that H is just being replaced by an R group. An amide is exactly what it sounds like. It's a carboxy carbon attached to an N group. So amide and amine, they have similar names. Just remember that amine has a single bond to carbon, and an amide has a single bond to a carbon that is also double bonded to an oxygen. And then an acid chloride, it's sort of similar. You can think of them as it's similar to a carboxylic acid, except instead of an OH group, we have a Cl group. All right? Okay. And so then the last big group of functional groups is groups with PO bonds. This is something that you'll get into more, such as biochemistry or other classes, when we have a monophosphate, diphosphate, triphosphate, or an acyl phosphate. You may remember triphosphate from adenoside triphosphate, ATP, which we use in our bodies for energy. That's an P, that's an R, ATP. And so in ACE, so you can see here that a monophosphate, we have one phosphate group, diphosphate, two phosphate group, triphosphate, three phosphate groups. And so then that is sort of a trend that you can sort of memorize, but it seems sort of self-evident in this case. And then in acyl phosphate, we have a CO bond or CO double bond attached to a phosphate group. So a carboxy carbon attached to a phosphate group. Okay. So now let's talk a little bit about how functional group can affect intermolecular forces. So we can see here in these two examples, we have isobutylene and acetone. These two, they're very similar, except isobutylene has a CH2 where acetone has an oxygen group. And if you notice, acetone is a ketone, and we can see that in the name because it's called acetone, which means it's a ketone. Okay? All right, so let's talk a little bit about how functional groups can change how a molecule reacts in its intermolecular forces. So we can see here straight off that we have a dipole-dipole moment in acetone. So there are three main intermolecular forces that we can talk about when we're talking about intermolecular forces. There's the first one, which is called van der Waals forces, which I will probably end up spelling wrong. I think it's two A's. And I will also call this VDR in my notes. VDW in my notes. We'll be talking about dipole-dipole, which I'll be talking about as DD in my notes. So DD. And then hydrogen bonding. I'm going to put H bonding. I usually refer to this as HB in my notes with a little line between them. Okay, so these three forces make up the intermolecular forces between a molecule and itself. So just a reminder, intermolecular forces are the forces between two of the same molecule. So it's like I have like a big pot of water. It's how the individual H2O atoms bind to, or not bind to each other, but attract each other and interact with each other. And so a good example of all this would be H2O itself. So let's first talk about van der Waals forces. This is also known as London dispersion forces. I just call it van der Waals. Some people call it London dispersion. Van der Waals forces are present in every single molecule. Essentially what a van der Waals force is, it's sort of the idea that when you have a compound, let's say this circle here is a compound, it has an electron cloud around it represented by these dots. And every millisecond, these different electrons are in different formations. And every now and again, these electrons will line up so perfectly that one side of the molecule has all of the electrons. So that side of that molecule is partially negative, and then the other side is partially positive. But this only happens like in 1 millisecond, in one moment for van der Waals forces. But every now and again, those forces of partial positive, partial negative in the electron cloud make those molecules attracted to each other. In a similar vein, we can talk about dipole-dipole forces, and I'm going to use water as my example. So a dipole-dipole force is essentially a permanent van der Waals force. So we see here that this oxygen is more electronegative than those hydrogens. A reminder, electronegative just means it attracts electrons more. So this oxygen is more electronegative than both of these hydrogens. So it's going to attract more of that negative charge, and it's going to be partially negative. Oh, and by the way, this little symbol here, this means partially, and then I'll put a positive or a negative by it, and then it would be partially positive or partially negative, okay? And so now we can see that that oxygen is partially negative, and so then these hydrogens would be partially positive. This is similar to van der Waals, except this dipole-dipole moment is permanent. And we can see here that if we put two water molecules next to each other, the partially positive charge of one hydrogen on one water molecule will be attracted to the partially negative charge on an oxygen in another water molecule. So in this case, these dipole-dipole forces can attract the two molecules of the same thing together, which makes them have stronger intermolecular forces. Okay? And so now let's talk about hydrogen bonding. Oh, and also the way that I'm discussing these are in the same order as their strength. Van der Waals is the weakest form of intermolecular forces, then dipole-dipole, and then hydrogen bonding. Hydrogen bonding occurs whenever you have an OH bond, an NH bond, or an FH bond. And we can see this the most in DNA. So you know DNA is made up of a bunch of different amino acids, or not amino acids, sorry, that's proteins. They're made up of different nucleic acids. So the way that these nucleic acids hold on to each other is through hydrogen bonding. So what occurs in hydrogen bonding, so let's say that we have an OH right here, and then an OH right here on the same molecule, and then like there's an R group over here on each of the oxygens. In this bond, we can see that oxygen is going to be partially attracted to the hydrogen on the other molecule, and hydrogen is going to be partially attracted to the oxygen on the other molecule, which attracts them together and is a very powerful intermolecular force, which makes hydrogen bonding the strongest, the most influential intermolecular force. Okay? So now why are we talking about these intermolecular forces? Well, if we go up and go back to comparing isobutylene and acetone, we can see that isobutylene only has van der Waals, whereas acetone has van der Waals and a dipole-dipole. So acetone is going to experience higher levels of intermolecular bonding, and thus it will have a higher melting point and a higher boiling point. If the molecules are more attracted to each other, they're going to hold on to each other more tightly. They're not going to be as prone to dissipating into the air, such as with boiling point, or melting into a liquid, such as with a solid going to a liquid. Okay, and so then that's why this is important. The intermolecular forces determine the boiling point and the melting point of different types of molecules. Okay, and one more thing to note about van der Waals forces is the bigger your molecule, the more the van der Waals is going to affect it. And so we can see here in this example with butane, pentane, and hexane. Hexane is by far the biggest here, C6H14. And so we can see it has the highest boiling point when compared to pentane, which is C5H12, and butane, C4H10. So we can see here that with increasing surface area, the boiling point also increases because the van der Waals forces are increasing overall. Okay. So now let's move on a little bit. And then now we can talk about functional groups and reactivity. Again, like I said before, the functional groups is what makes a carbon-based compound reactive. So this is what we're going to be talking about for most of the rest of the class. The functional groups cause carbon-based molecules to be reactive, and we can see here that in this case with the chlorine and the oxygen here, or the OH group, the hydroxy group, and the chlorine or the halide group here, they make the carbon they're attached to partially positive, which will make it more susceptible to be attacked by something called a nucleophile, which just means something that's nucleus loving. I spelled nucleus wrong. Nucleus loving / positive charge loving. Okay, and on the flip side, we have electrophiles, which are electron loving, negative charge loving, which we talked about a little bit before in the acid base chapter. And again, we'll go on into it more when talking about further organic reactions. And we can see here that we have different nucleophiles, different pi bonds. All of this stuff is what causes reactions to occur in organic chemistry. And this is what we're going to be focusing on. And you don't have to memorize any of this yet for this class, because we will talk about each one of these more individually in further chapters. And here's the example of hydrogen bonding in DNA that I talked about a little bit before. We can see that with guanine and cytosine, we have 3 hydrogen bonds here. So we have oxygen bonding or being attracted towards H being attracted towards N, H being attracted towards O. And then in adenosine and thymine, we have two moments of hydrogen bonding. And if you think about it here, which one of these is going to have a higher boiling point, a higher melting point? It's going to be the one with 3 modes of hydrogen bonding, because those intermolecular forces are stronger. And so overall, they're going to have a higher boiling point. And this is why being able to tell things apart. And then we can think about if we have a DNA molecule that's made up of more guanine than adenosine, then we can tell that, oh, it's going to be more stable. It's going to be less likely to not dissolve, but melt or boil off. And so that's why understanding intermolecular forces is important, at least when we're talking about biology and biomedical sciences. Okay, so again, this is going over a boiling point, and here are some different examples of boiling point. We can see here, try to pause the video and try to name what intermolecular forces that we have here. I'm just gonna go ahead and do it. Pentane has van der Waals and nothing else. Butanol has van der Waals, and we can see here that this oxygen atom is electronegative, more electronegative than carbon, so it's going to pull the negative charge towards itself, make it partially negative, and the carbon it's attached to partially positive. So this one also has dipole-dipole forces. And finally, we can see butan-1-ol. It has van der Waals. It also has a mode of dipole-dipole, but that's less important than seeing this hydrogen bonding right here. So we see that butan-1-ol, it has a higher boiling point because it has more intermolecular forces than butanol, which has more more intermolecular forces than pentane. And so you should be able to do that when given 3 molecules. Okay, so here are some examples. Oh, and one more thing to note about melting point is usually you will go by the different intermolecular forces, but sometimes when they have the same amount of intermolecular forces, like here, they both only have van der Waals forces, van der Waals, van der Waals. The one that can more tightly pack together or more orderly pack together, such as in this case, 2,2-dimethylpropane, they're smaller, they're easier to fit into each other. So 2,2-dimethylpropane, because it's more orderly, it can fit in with each other more closely, it's going to have the higher melting point than something that's a little bit more, that takes up a little bit more space, such as 2-methylbutane. So you can see here that it's like almost the opposite of boiling point when we're talking about when you have more surface area, you have a higher boiling point. So it's sort of the same thing, but opposite. All right, so let's just continue on. And there's one more thing that we need to talk about in this chapter, and that's called solubility. So recall in Gen Chem where we talked about polar solvents can dissolve polar compounds. So water, H2O, water is probably the most famous polar solvent. Oxygen partially negative, hydrogen partially positive on both sides. And we know that water can dissolve something like salt, NaCl. NaCl is an ionic compound, which means it has a very large dipole-dipole. It's very polar. So a polar compound or a polar solvent will be able to dissolve this polar compound. On the other hand, let's say that we just had something like cyclohexane. So I'm going to draw cyclohexane. There are no molecules there that will make a dipole moment because carbon and hydrogen are so close in electronegativity. They are going to have roughly the same pull in each other. There's not going to be a dispersion of that negative charge. So this is not going to be able to be dissolved in a polar solvent. However, it will be able to be dissolved in a non-polar solvent, okay? And so the general rule of thumb when we're talking about solubility is that if we have a carbon compound that is 5 carbons or less, so if I had like this guy right here, 1, 2, 3, 4, 5 carbons, and then an oxygen to offset those carbons, generally it will be able to be dissolved in a polar solvent such as water. So you can see here in this example, we have 1, 2, 3 carbons attached to one hydroxy group. So that means it's going to be soluble in water and soluble in an organic solvent because we have this big organic tail right here. Okay, so overall, if you're soluble in water, you are polar. If you are soluble in organic solvents, you are non-polar. All right. Okay, so that wraps it up for today for organic functional groups. Again, let me know if you have any additional questions. I'm always open to talk. I will see you guys next time.